According to ANSI/TI-800.40, the following grounding practices are acceptable for telephone services. Firstly, bonding to a properly installed electric utility electrode. Secondly, bonding to a grounding electrode system that meets the requirements of the National Electrical Code, also known as the NEC. Thirdly, bonding to the electrical service mast where the electric utility has granted permission and an acceptable connection is available. It's important to note some exceptions. The NEC does not specifically require grounding electrodes for aerial electric services. However, some electric utilities may have their own requirements for grounding aerial services. If there is no electric utility electrode or grounding system available, the best practice is to contact the customer and advise them of the situation. Recommend that the customer have an electrician install a grounding electrode. Do not proceed with work until the grounding issue is resolved. The rationale behind this is that bonding to the electrical service mast without the utility's permission or an acceptable connection could create a safety hazard. Additionally, if the electric service mast is not properly grounded, it may not provide an effective path to ground for the telephone service. By following the recommended practice, you are ensuring the safety and the integrity of the telephone service. Grounding is a critical aspect of electrical and telecommunications installations. Its primary purpose is to provide a safe path for electrical fault currents to return to the source, thereby minimizing the risk of electric shock and fire. In the context of telephone services, proper grounding ensures the safety of technicians, customers, and the integrity of the telecommunications network. The ANSI/TI-800.40 standard outlines specific requirements for grounding telephone services. This standard references the NEC, which provides comprehensive guidelines for electrical installations, including grounding and bonding. When a technician encounters a situation where there is no existing grounding electrode system, it is crucial to adhere to established safety protocols and industry best practices. As previously mentioned, acceptable grounding practices for telephone services include bonding to a properly installed electric utility electrode. This is often the preferred method, as the electric utility's grounding system is typically robust and well maintained. Bonding to a grounding electrode system that meets the requirements of the NEC is another acceptable practice. This involves installing a grounding electrode, such as a ground rod, ground plate, or concrete encased electrode, and connecting it to the telephone service equipment. Bonding to the electrical service mast is permissible only when the electric utility has granted permission and an acceptable connection is available. This practice should be approached with caution, as the service mast may not always provide an adequate grounding path. The NEC provides detailed requirements for grounding electrode systems, including the size and type of grounding conductors, the depth and location of grounding electrodes, and the bonding of various metallic components. These requirements are designed to ensure that the grounding system is effective in providing a low impedance path for fault currents. In situations where there is no electric utility electrode or grounding system available, it is imperative to take a conservative approach. Contacting the customer and advising them of the situation is the first step. Explain the importance of proper grounding and the potential safety hazards associated with an ungrounded system. Recommend that the customer have a qualified electrician install a grounding electrode. Emphasize that this is necessary to ensure the safety of the telephone service and comply with applicable codes and standards. Under no circumstances should the technician proceed with the work until the grounding issue is resolved. Attempting to bond to the electrical service mast without the utility's permission or an acceptable connection could create a dangerous situation. The service mast may not be properly grounded, and it may not be able to handle the fault current from the telephone service. This could result in electric shock, fire, or damage to equipment. Moreover, even if the service mast appears to be grounded, it may not provide an effective path to ground for the telephone service. The impedance of the grounding path may be too high, which could limit the flow of fault current and increase the risk of electrical hazards. By following the recommended practice, you are prioritizing safety and ensuring the long-term reliability of the telephone service. A properly grounded system will protect against electrical faults, minimize the risk of electric shock, and prevent damage to equipment. In addition to the ANSI/TI-AMINUS 800.40 standard and the NEC, there may be local codes and regulations that apply to grounding telephone services. It is important to be familiar with these requirements and to comply with them at all times. The grounding electrode conductor, often referred to as the GC, plays a vital role in the grounding system. The size of the GC is determined by the size of the service entrance conductors, as specified in NEC Table 250.66. For example, if the service entrance conductors are 2/0 copper, the minimum size GC would typically be number 4 copper. The grounding electrode itself should be selected and installed in accordance with NEC requirements. Common types of grounding electrodes include ground rods, which must be at least 8 feet long and driven into the earth, ground plates, which must have a surface area of at least 2 square feet, and concrete encased electrodes, which must be at least 20 feet long and encased in concrete. The location of the grounding electrode should be carefully chosen to ensure that it is in contact with the earth and that it is protected from damage. The electrode should be located as close as practicable to the service entrance equipment. Bonding is another critical aspect of grounding. Bonding involves connecting various metallic components together to create a low impedance path for fault currents. This includes bonding the service equipment, the grounding electrode system, and any metallic piping systems. The bonding conductors must be sized in accordance with NEC Table 250.102. Proper bonding helps to ensure that all metallic components are at the same electrical potential, which reduces the risk of electric shock. In addition to the grounding electrode conductor and bonding conductors, other important components of the grounding system include ground clamps, connectors, and enclosures. These components must be listed for the intended use and must be installed in accordance with the manufacturer's instructions. Regular inspection and maintenance of the grounding system are essential to ensure its continued effectiveness. The grounding electrode and connections should be inspected periodically for corrosion or damage. The grounding conductors should be checked for proper size and condition. Any deficiencies should be corrected promptly. It is also important to verify the continuity of the grounding system using a ground resistance tester. This will help to identify any high resistance connections or breaks in the grounding path. When working with electrical and telecommunication systems, it is always important to follow safe work practices. Wear appropriate personal protective equipment, such as gloves and eye protection. To energize equipment before working on it whenever possible. Use insulated tools. And never work alone. In the specific scenario described, where the technician found that there was no bond to the electric utility electrode and no ground at the service disconnect, it is crucial to take immediate action to address the safety hazard. The technician should not proceed with any work until the grounding issue is resolved. The customer should be advised to contact a qualified electrician to install a grounding electrode system. The electrician should be familiar with the NEC requirements for grounding and bonding and should be able to install a system that meets the applicable codes and standards. Once the grounding system is installed, the technician can then proceed with the telephone service installation, ensuring that the telephone service equipment is properly bonded to the grounding system. In addition to the technical aspects of grounding, it is also important to consider the legal and regulatory requirements. Many jurisdictions have adopted the NEC as law, which means that compliance with the NEC is mandatory. Failure to comply with the NEC can result in fines, penalties, and even criminal charges. Therefore, it is essential to be familiar with the applicable codes and standards and to ensure that all work is performed in accordance with these requirements. Grounding is not simply a matter of connecting a wire to a metal rod. It is a complex and critical aspect of electrical and telecommunications safety. By understanding the principles of grounding, following the applicable codes and standards, and adhering to safe work practices, you can help to ensure the safety of yourself, your customers, and the public. The NEC is updated every 3 years, so it is important to stay current with the latest requirements. Changes to the NEC can affect the way that grounding systems are designed and installed. Therefore, it is essential to participate in continuing education and to stay informed about the latest developments in the field. Grounding is an essential element of electrical safety in telecommunications infrastructure. The procedures and guidelines outlined in standards like ANSI/TI 800.40 and the NEC are designed to protect people and property from electrical hazards. Let's delve deeper into specific scenarios and considerations. Firstly, let's consider the scenario where a technician arrives at a customer's location and finds that there is no grounding electrode system in place. This could be due to a variety of reasons, such as the age of the building, the type of construction, or previous renovations. In this situation, the technician should immediately assess the situation and determine the best course of action. As previously stated, the recommended practice is to contact the customer and advise them of the situation. The technician should explain the importance of proper grounding and the potential safety hazards associated with an ungrounded system. The technician should then recommend that the customer have a qualified electrician install a grounding electrode system. It is crucial to emphasize that this is not something that the technician can or should do themselves. Installing a grounding electrode system requires specialized knowledge and skills, and it must be done in accordance with the NEC and other applicable codes and standards. Once the customer has contracted with an electrician to install a grounding electrode system, the technician can then proceed with the telephone service installation. However, before doing so, the technician should verify that the grounding electrode system has been properly installed and that it meets the requirements of the NEC. This may involve inspecting the grounding electrode conductor, and the bonding connections. If the technician finds any deficiencies, they should notify the electrician and request that they be corrected before proceeding with the telephone service installation. Now let's consider the scenario where there is a grounding electrode system in place, but it appears to be inadequate or improperly installed. For example, the grounding electrode conductor may be too small, the grounding electrode may be corroded, or the bonding connections may be loose. In this situation, the technician should again assess the situation and determine the best course of action. If the technician is qualified to evaluate the grounding electrode system, they may be able to make recommendations for improvements or repairs. However, if the technician is not qualified, they should again recommend that the customer contact a qualified electrician. The electrician can then evaluate the grounding electrode system and make any necessary repairs or upgrades. It is important to note that even if there is a grounding electrode system in place, it may not be adequate for the telephone service. The telephone service may require a dedicated grounding electrode system to ensure proper performance and safety. In this case, the technician should recommend that the customer install a separate grounding electrode system for the telephone service. Now, let's discuss the different types of grounding electrodes that are available. The most common type of grounding electrode is the ground rod. Ground rods are typically made of copper or copper-clad steel, and they are driven into the earth to a depth of at least 8 feet. Ground rods are relatively inexpensive and easy to install, making them a popular choice for residential and commercial applications. Another type of grounding electrode is the ground plate. Ground plates are typically made of copper or steel, and they are buried in the earth to a depth of at least 2 feet. Ground plates have a larger surface area than ground rods, which can make them more effective in certain soil conditions. A third type of grounding electrode is the concrete encased electrode. Concrete encased electrodes are typically made of copper wire or rebar, and they are encased in concrete that is in direct contact with the earth. Concrete encased electrodes are often used in new construction as they can be easily integrated into the building's foundation. The choice of grounding electrode will depend on a number of factors, including the soil conditions, the available space, and the cost. The electrician can help the customer choose the best type of grounding electrode for their specific application. In addition to the grounding electrode conductor is also an important component of the grounding system. The grounding electrode conductor connects the grounding electrode to the service equipment. The size of the grounding electrode conductor is determined by the size of the service entrance conductors, as specified in NEC Table 250.66. It is important to use the correct size grounding electrode conductor to ensure that the grounding system is effective in providing a low impedance path for fault currents. The grounding electrode conductor must be securely connected to the grounding electrode in the service equipment. The connections must be made using listed connectors that are suitable for the application. The connections should be inspected periodically to ensure that they are tight and free from corrosion. Bonding is another critical aspect of grounding. Bonding involves connecting various metallic components together to create a low impedance path for fault currents. This includes bonding the service equipment, the grounding electrode system, and any metallic piping systems. The bonding conductors must be sized in accordance with NEC Table 250.102. Proper bonding helps to ensure that all metallic components are at the same electrical potential, which reduces the risk of electric shock. The bonding connections must be made using listed connectors that are suitable for the application. The connections should be inspected periodically to ensure that they are tight and free from corrosion. In addition to the technical aspects of grounding, it is also important to consider the legal and regulatory requirements. Many jurisdictions have adopted the NEC as law, which means that compliance with the NEC is mandatory. Failure to comply with the NEC can result in fines, penalties, and even criminal charges. Therefore, it is essential to be familiar with the applicable codes and standards and to ensure that all work is performed in accordance with these requirements. Grounding is not simply a matter of connecting a wire to a metal rod. It is a complex and critical aspect of electrical and telecommunications safety.